ground fault protection is indeed required in the next downstream breaker for panels after the main in hospitals. The 2020 National Electrical Code, specifically Article 517, which pertains to healthcare facilities, mandates ground fault circuit interrupters, or GFCIs, in all patient care areas, wet locations, and other specified areas. This requirement is further detailed in Article 210.8 Burn, which states that ground fault circuit interrupters shall be installed on the line side of equipment rated 125 volts, single phase. These GFCIs are installed to provide protection to personnel. The fundamental intent of this requirement is to establish a robust level of protection against electrical shock. This is achieved by rapidly interrupting the electrical circuit in the event of a ground fault. By installing GFCIs on the next downstream breaker for panels following the main, essentially all circuits downstream from that main breaker are afforded the protection offered by GFCIs. It's important to acknowledge that there can be exceptions to this overall requirement, and these exceptions are contingent upon the specifics of each individual application. For instance, GFCIs are typically not mandated on circuits that supply equipment that is not easily accessible to patients or healthcare staff. Examples of such equipment might include HVAC systems or fire alarm systems. To delve deeper into the specifics of ground fault protection within hospital electrical systems, it's beneficial to understand what a ground fault is and how a GFCI operates. A ground fault occurs when there is an unintended electrical path from a hot conductor to ground. This can happen if insulation fails, a wire comes loose and contacts a grounded metal surface, or any other scenario where electricity deviates from its intended path and finds a way to ground. Ground faults are dangerous because they can cause electrical shock if a person comes into contact with the energized surface and ground. They can also lead to fires if the fault current is high enough to ignite nearby materials. A GFCI is a device designed to detect these ground faults and quickly interrupt the circuit, preventing electrical shock and reducing the risk of fire. It works by monitoring the current flowing in the hot and neutral conductors of a circuit. Under normal conditions, these currents should be equal. However, if a ground fault occurs, some of the current will leak to ground, creating an imbalance between the hot and neutral conductors. The GFCI detects this imbalance and trips the circuit, typically within a fraction of a second. Now, let's examine the specific requirements of Article 517 and Article 210 of the NEC in more detail. Article 517, Healthcare Facilities, provides comprehensive guidelines for electrical installations in hospitals, nursing homes, clinics, and other healthcare settings. This article recognizes the unique electrical safety needs of these facilities, where patients may be particularly vulnerable to electrical shock due to their medical condition or the use of sensitive medical equipment. Article 517.13 requires that all electrical equipment in patient care areas be listed and labeled for the intended use. This ensures that the equipment meets specific safety standards and is suitable for use in a healthcare environment. Furthermore, Article 517.19 requires that all receptacles in patient care areas be hospital-grade. Hospital-grade receptacles are designed to be more durable and reliable than standard receptacles, and they are subjected to rigorous testing to ensure they can withstand the demanding conditions of a healthcare environment. Article 517.20 provides detailed requirements for ground fault protection in patient care areas. This section mandates the use of GFCIs in specific locations, such as wet locations and areas where patients may be in contact with conductive surfaces. The goal is to minimize the risk of electrical shock to patients and staff. Now let's turn our attention to Article 210, which covers branch circuits. Article 210.8b specifically addresses GFCI protection for personnel in dwelling units and other locations. As previously mentioned, Article 210.8 Bone requires GFCI protection for all 125-volt single-phase receptacles installed in bathrooms, kitchens, garages, and other specified locations. This requirement is intended to protect people from electrical shock hazards in areas where they are likely to be exposed to water or other conductive materials. The NEC also provides exceptions to the GFCI requirements in certain situations. For example, GFCIs are not required for receptacles that are not readily accessible or that serve appliances that are unlikely to pose a shock hazard. However, it's important to carefully evaluate each situation to determine whether an exception applies. It's important to understand the terminology related to ground fault protection. Firstly, a ground fault circuit interrupter, or GFCI, as previously mentioned, is a device that protects people from electrical shock by detecting ground faults and quickly interrupting the circuit. Secondly, an arc fault circuit interrupter, or FSI, is a device that protects against electrical fires by detecting arc faults, which are dangerous electrical discharges that can occur due to damaged or worn wiring. Thirdly, ground fault protection of equipment, or GFP, is a system that protects equipment from damage due to ground faults. GFP systems typically use a current transformer to monitor the current flowing in the grounding conductor. If the current exceeds a certain threshold, the GFP system will trip the circuit breaker, preventing damage to the equipment. Another consideration is selective coordination. Selective coordination is the practice of designing an electrical system so that only the overcurrent device closest to a fault will trip, leaving the rest of the system operational. This is particularly important in hospitals, where it's crucial to maintain power to critical equipment during a fault. To achieve selective coordination, engineers must carefully select the appropriate overcurrent devices and coordinate their tripping characteristics. This involves considering the fault current levels, the time current curves of the overcurrent devices, and the overall system configuration. There are several methods available for achieving selective coordination. One common method is to use fuses and circuit breakers with different interrupting ratings and tripping characteristics. Fuses are typically faster acting than circuit breakers, so they can be used to protect downstream circuits while allowing upstream circuit breakers to remain closed. Another method is to use zone-selective interlock systems, which allow circuit breakers to communicate with each other and coordinate their tripping. Zone-selective interlock systems can provide very fast and selective tripping, minimizing the impact of a fault on the rest of the system. In addition to the NEC requirements, hospitals may also have their own internal standards and procedures for electrical safety. These standards may be more stringent than the NEC requirements and may include additional safety measures, such as regular electrical inspections and training for staff. It's crucial for healthcare facilities to establish a comprehensive electrical safety program that addresses all aspects of electrical safety, from design and installation to maintenance and training. This program should be based on the NEC and other applicable standards, and it should be regularly reviewed and updated to ensure its effectiveness. Here are some specific examples of where GFCI protection is typically required in hospitals. Firstly, all receptacles in patient bathrooms and kitchens. Secondly, receptacles within 6 feet of sinks or other wet locations in patient care areas. Thirdly, receptacles serving infant incubators and other sensitive medical equipment. Fourthly, receptacles in operating rooms and other critical care areas. Fifthly, receptacles in areas where patients may be in contact with conductive surfaces, such as metal beds or exam tables. Now, let's discuss some of the potential challenges in implementing ground fault protection in hospitals. One challenge is the cost of GFCI devices. GFCIs are typically more expensive than standard receptacles and circuit breakers, so the cost of installing them throughout a hospital can be significant. However, the cost of GFCI protection is a small price to pay compared to the potential cost of an electrical shock or fire. Another challenge is the potential for nuisance tripping. GFCIs can sometimes trip due to minor electrical disturbances, such as voltage fluctuations or electromagnetic interference. This can be disruptive in a hospital environment where it's crucial to maintain power to critical equipment. To minimize the risk of nuisance tripping, it's important to select high-quality GFCI devices and to properly install and maintain the electrical system. Furthermore, regular testing of GFCI devices is essential to ensure they are functioning properly. The NEC requires that GFCIs be tested monthly to verify their functionality. This can be done using a GFCI tester, which simulates a ground fault and verifies that the GFCI trips the circuit. In addition to GFCI protection, Hospitals also need to implement other electrical safety measures, such as regular electrical inspections, proper grounding and bonding, and surge protection. Regular electrical inspections can help identify potential hazards, such as damaged wiring or overloaded circuits. Proper grounding and bonding can help prevent electrical shock by providing a low impedance path for fault current to flow back to the source. Surge protection can help protect sensitive electronic equipment from damage due to voltage surges caused by lightning or other events. It's important to note that ground fault protection is not a substitute for other electrical safety measures. It's just one component of a comprehensive electrical safety program. To ensure the safety of patients and staff, hospitals must implement a multifaceted approach to electrical safety that includes GFCI protection, regular inspections, proper grounding and bonding, surge protection, and ongoing training for staff. In conclusion, ground fault protection is a critical safety measure in hospitals. By installing GFCIs in accordance with the NEC requirements, healthcare facilities can significantly reduce the risk of electrical shock and fire, protecting patients and staff from harm.